Hi thinkers, welcome to the object-oriented design course on Thinkix Academy. In this tutorial, we are going to cover a very important topic, which is UML for object-oriented design. In this tutorial, we are going to see how we can use a modeling language to actually represent some design patterns and to also represent a whole software architecture, which is by using classes. So basically, we are going to study the UML class diagrams, which represents the classes and how they are related with each other, and there are a bunch of things that we're going to do. The main reason why we do that is to actually create a model so that it is easy to visualize that, and it becomes easy for us as the developers to understand how the objects of one class are related to objects of the other class, and it helps in a lot understanding with some design patterns also. So we will be using this model language a lot in the upcoming videos of this course, where we will be studying the design patterns. We will use this whole language to implement and to model the classes, right? So let's start with the tutorial. Let's start with UML. So UML basically stands for the Unified Model Language. As it says, it's a language for modeling, right? Now there are three parts of UML. The first part is to create or construct a whole class structure. The second part is this part, which actually represents the relationships of one class with the other class. And the last part is the cardinality, which represents how many objects are related to the objects of the other class, right? So there are three parts. We will study them one by one. Let's start with the first part, which is the representation of a particular class. In a software, we will have multiples of classes. There will be a lot of classes. So let's start by constructing only one class, which has all the required attributes and all the things that we can consider. And we can apply the same concept in considering some other classes as well, right? So this class is a class shape. So the first thing is you need to create a box and three partitions in it. The first partition represents the name of the class. So I'm going to write here that it represents the name of the class, right? The second partition, which is this one, represents the variables that are there inside of this class, right? So this class has three variables: color, border, and there is one more variable, which is attribute. Now we will use colon to and we will specify the data type of these variables, right? So here you can see that string, integer, and this shape is actually the data type of the color, border, and attribute. So you can see that string is the data type of color. So we have a string color variable inside of a class shape, right? Similarly, we have an int border, and similarly we have a shape attribute. Now you can observe there are three symbols here which represents something. The plus symbol represents that it is a public member. The minus symbol represents that it is a private member, right? The last one, which is this hash symbol, represents that it is a protected member. So this means that color is a public member, so it is actually public string color. The border is a private member, so private int border. The last one is protected, so protected shape attribute. So now we have seen, we are now understanding the simple concept that we are creating a model of the shape class, and now we are done with the variables and name of the class. The last part is obviously the functions inside of this class. So I'm going to write here the functions. All the functions goes into this last partition of this model, right? Similar to the variables, we have these symbols again, plus, minus, hash symbol. These represent whether the function is a public function, private function, or a protected function, right? It's very simple. The last one, which is here also, you can see a colon is here that represents string, float, and this one more variable. So this represents what will be the data type of the return object from this function, right? So let's say we have a function. Let's say we have a function public int, and let's say we have a border function, right, which gives us the border. So this function has a return type integer, so it means that it is going to return an integer, right? So what will be the representation here? Instead of string, I will write integer. If it is a string, I will write here string, and similarly if it is a float, I will write it a float. The last one here you can see is different from this. This represents a circle data type. So it may happen that you are actually returning a reference to some other class. Let's say the class is circle here. Since we are returning the reference to that class, right, we are marking a star here, and the star means that we have a reference to that data type, right, which is circle in our case. So now we have studied this part, right? We have studied these symbols. We have studied that, okay, this part represents the return type, right? So this part actually represents the return type. Let's move on to the function. Here we have the function name. So function 1 is one function inside of this class. We have function 2, we have function 3, right? We have these three functions. Inside these three functions, we will also have some arguments. So let's say there is a border function. It will have some input parameters, and you can just see that we have these parameters here, a1 and a2. And what is the type of what is the data type? A2 has a data type integer, and a1 has a data type float, right? So you can see that we use colon to represent the data type. So here A1 has a data type float, A2 has a data type integer. Now you can see there are three variables here which I am going to mark as red because they are very important, which is in, then in out, and then out, right? So I have these three variables. So what is the meaning of in? In means that the caller has given this argument A1 to this function 1, right? So in order to understand this clearly, what I'm going to do is I'm going to give you a very simple example, right? Let's say I create a shape of this class shape. So let's say the object of this class shape is shape object, and let's say I want to call this function f1, right, which is function 1, which is fun, and here it will be 1, right? Now inside this function I'm passing a1 as the argument, right? So this is actually the function call. So if at the time of function call I give an argument, I'm passing this argument to this class, I'm going to say that this is actually in, right? Now let's move on to in out. What will happen if the function gives an input, right? We say it's in, right? So in out actually consists of two terms, in and out, right? So in, we have already studied in means that we are passing the argument at the time of function call. What is the meaning of out? Out means that this function will perform some modifications of the input, and it is also going to give the same output, which is a1, outside of this function, right? So this will be actually the input which is given by the function call, and this is the output to the function call, right, which is also the return type, right? So return value. So whatever value this function fun1 will return, if it returns something which we have given to it, right, if it returns a value, we will say it is out, right? So we have in out, we have now studied in and in out. Let's start with the last one is out. So out means that we are not passing any object to this function. So I'm going to remove this call, and let's consider this call, which is the f3 function. Again, I will use the object of shape class dot f3. Now you can see at the time of function call, I am not passing any arguments, right? So in is not there. Now you can see out is here. Out means that this function is going to give an output, right? So this function f3 will be defined like this. So you can see it's a hash symbol. So hash means protected. The name of the function is f3. There are no inputs given to the function, but this function will return a circle type. So I'm going to actually write it like this. So protected, then I have circle, which is a reference, right? This star means reference. Now we have this function f3, which takes no input, but it gives the output a3. So inside of this function, we will have a variable a3, right? Let's say it actually represents something, and we are going to return this out of this function. So we modify this function and we return it out. So that's why we call it as a out a3, right? So these are three important notations. In means it only goes inside of the function, and in out means it goes inside of the function and comes out of the function. But out means that it only is coming out of this function, right? So we have covered these three cases, and this is the whole thing about the class diagram, and this is how you are going to represent classes inside UML, right? This is a very useful diagram because in this diagram only I don't need to see the code or the expressions. I can just see this diagram and I can tell about everything about this class shape, right? So now we are going to cover the next part, which is the relationship among different classes. So now I'm going to remove this whole class diagram here because we need to study these relationships. So these are the major 6 relationships inside of UML that we are going to study, and it is very important to study them. And for each one of them, I'm going to give you a separate example of what is the use case of a particular relationship. And then finally, we will cover the last part, which is the cardinality, right? Now, just consider this part. In these, you can see we have already studied some of the relationships. For example, we have already studied inheritance. So we know that inheritance means the child class inherits some of the properties of the parent class. That is clear to us. So let's say there is a class shape, and this class shape is here, and we have a class circle, and this class circle inherits the properties of the shape class. So I'm going to draw this type of relation. So it is represented by this arrow, which you can see here, right? So it inherits. So we will have this type of arrow. Now observe that this arrow has this empty here. It's not filled with some color. It only has the border. And it is actually very important that inheritance means that we have a single dotted, not a dotted line. It will be a full line, and we have this arrow. So this means that the circle is inheriting the properties of shape class, right? So we have already studied that. Now I will remove this. Now let's move on to the next one, which is dependency, right? We have also studied dependency. So dependency means that one object is dependent on the other object, right? So let's say there is an object 1, and this object is dependent on the other object 2, right? So I'm going to write a dotted line here, and then I will write it. I will draw an arrow like this. So you will have to make sure that the arrow is same as I've drawn here. Do not confuse between them. This is the only model language that we have to follow. These are the rules of the model language. So you can say that object 1 is dependent on object 2. Now you can see this is a dotted line, not a full line, right? Like this, right? Not a solid line like this. So when we have a dotted line, we say that one object, although it is dependent on another object, it is not holding a strong relationship. So dotted line means the relationship between the object is actually not very strong. It is a weak relation. Let me give you a very simple example. Let's say we have a supplier who supplies some good and there is a consumer which consumes some good, right? Now I ask you a question, is a supplier dependent on consumer or is a consumer dependent on supplier? The answer is yes, because if the consumer wants to consume something, it needs to get something from the supplier. So we can also say that supplier is dependent on consumer also, because if the consumer will have the demand, then only the supplier will be able to supply. Now, is this relationship a strong relationship? The answer is no, because it may happen that if this consumer disagrees that I'm not going to take supplies from you, the supplier will supply to some other consumer as well, right? So there can be multiple consumers. So this relationship is not that strong. It is a, you can say, a weak relationship. So if the dependency is not strong, we are going to use a dotted line and this arrow, and we are going to say that this object is dependent on consumer, but the relationship is not that much strong. Then the relationship is very strong. We are going to call it association. We will study that also, but first I just want you to concentrate on dependency. We have already covered inheritance and now we have covered dependency, right? So this example is an example of dependency, and the relationship between the supplier and the consumer is weak because there can be multiple suppliers and even multiple consumers, right? So now I'm going to remove this example, and now we're going to come to the next relationship, which is the realization relationship, right? Which is this one. Realization is, again, you can see dotted line. It means there is a weak relationship. So let's say we have a class shape, right? We're going to take the same example of shape, and let's say there is a class rectangle, or let's say there is a class area, or let's just make this rectangle only. And let's say there is a function inside of this shape class, which is actually a draw function. Now let's say that this is not a shape, this is an interface. So if this is an interface, we are going to write it like this, and we can write that this is an interface, and these double arrows are used to represent that this is an interface. So if this rectangle class implements the functions of this interface, we can say that there is a realization, right? So I can write dotted lines and this arrow symbol, right? Same as this one. So we can say that rectangle realizes draw function from shape, right? So it's very simple to understand that if we have a class that implements the functions of the other class or an interface, we say that the relationship is realization, because the rectangle is realizing the draw function which existed inside of the shape interface. So this type of relation is known as a realization in dependency, right? The realization relationship. So now I'm going to remove this one example, and let's now consider the remaining three examples, and these are very important, which is association, aggregation, and composition. And there is a lot of confusion among these three. We're going to just solve the confusion out. We're going to sort that confusion out, and we will see how these three are related to each other and how they are not related to each other, right? So we can sort out, we will take some examples that are examples of one and not example of others, right? So in order to explain these three concepts, it's very easy. First, I will draw a circle here, big circle. This circle represents association relationship, right? So let's say we have some examples inside of the circle that are an example of association relationship. Out of some of these examples, we may have some examples which are an examples of aggregation, right? So out of these examples, there are some examples which are examples of aggregation. Out of these examples of aggregation, there will be some examples of composition, right? So here we have the examples of composition. So this is a very important diagram because it actually helps us in finding out what is the relationship between two classes, right? So whenever I say the relationship between two classes, you need to remember that classes does not have relationship. The objects of the classes have relationship, right? So let's say we have a class 1, we have a class 2. We cannot say that class 1 is related to class 2. We can say that the object of class 1 is related to object of class 2, right? Okay, so now let's start with some examples of these three so that we can understand clearly what exactly are they, right? Let's start with composition first. So I can think of a very simple example of composition, which is the car engine problem, right? So let's say we have a class car and we have a class engine. We need to ask one question from us. So if I want to derive the relationship between this car and engine, I will first answer this whether it is a composition. If it is a composition, then I will have to check whether it is aggregation. If it is aggregation, then I'm going to say that class car is and it has a relationship of aggregation with engine. If we then we will move towards association. So actually what we are trying to do is we are trying to go from the smaller circle and then we are going to the bigger circle, right? And that is exactly how we are going to understand what is the exact relationship. So if at any point we understand that okay, aggregation is not there, we fall back to the inner circle and we will say that the relationship between two objects is this one, right? So let's study the car engine problem. Now composition is also known as a part of relationship or a part whole relationship, right? So can I say engine is a part of car? Can I answer this question? The answer is yes, engine is a part of car, right? So if I can say that engine is a part of car, composition is there, right? So composition holds true in our case. So I'm going to write here composition is true, right? For composition I have this diagram which I can easily draw here, right? Something like this. So composition is there, but we will not stop at this point, right? It may have aggregation, right? So now we'll have to study aggregation. Let's see whether car and engine has the relationship of aggregation. Aggregation says has a relationship, right? So can I say car has an engine? The answer is yes, car has an engine, right? But there is a subtle difference between aggregation and composition. In composition, the composition relationship says that both of these objects, so I'm going to write an important point here, that in composition relationship and in aggregation, there is a very subtle difference, very simple difference. In composition, we say is that the objects will be dependent on each other and will not exist independently, right? So can we answer this question? So engine is a part of car. The answer is yes. So can car and engine, right? So this is the second question we will have to ask ourselves. Can car and engine exist independently? The answer is no, because an engine will have no use if it is not inside the car, right? So they are dependent, highly dependent on each other. So if they are highly dependent on each other, it means the relationship is composition. We move to aggregation and we say that in aggregation, we say that the objects have the ability to exist independently, right? So has a relationship is there. You can see car has an engine, right? Has a relationship is there, but the second question is false. Can car and engine exist separately? No. So if they cannot exist separately, aggregation is not true, right? So if aggregation is not true, we are not going to move to the outer circle. We will fall back and we will say that the relationship between car and engine is a composition relationship and not an aggregation relationship, right? So this is the first thing. Now let's take an example of aggregation. This was a classic example of composition. Now let's take an example of aggregation, and then we will take a simple example of association, right? So I'm going to just remove these, right? I'm just going to clean this up. And now let's take an example of aggregation. Let's say I have a class which is a class of phone list, right? So this is a class phone list and we have a class which is phone numbers, right? So the first class is a list of all the phone numbers. The second class is the phone number, right? So let's say that this is only phone number. So we have one phone number here, right? So let's start with composition, right? Let's answer the question part of or part whole, right? Part whole means it is a part of whole. So if I say phone list and phone number, can I say phone number is a part of phone list? The answer is yes. Phone number is a part of phone list. The second question is, can they both exist independently? The answer is yes. A phone number has its own existence. If we have a separate phone number, it is associated with some person and it can exist independently. And this phone list can also exist independently, right? It can have some other phone numbers as well. So we first go to composition. We check whether composition is there. The answer is yes. Composition is there because phone number is a part of the phone list, right? Then we move to aggregation. We say aggregation is there because phone list has a phone number and they can exist independently. So if they can exist independently, we can say that aggregation is there. Now we move to association, right? So association means, can these phone numbers, right? So are these phone numbers associated directly with the phone list? When we say associated, we mean a strong relationship. So do you see any strong relationship between this phone list and a particular phone number? The answer is no, right? So association is not there. So it means it is an example of aggregation. In aggregation, we will use this particular arrow to represent aggregation. Can you consider some more example of aggregation? You can consider an integer array, right? So let's consider a simple integer array, right, which is composed of integers. And let's say we have an integer here, right? And we can have multiple integers. So can I say integer is a part of integer array? Yes, it is a part of. Can I say that this integer array and this integer can exist independently? Answer is yes. It means aggregation is there, right? So I can aggregate a lot of integers and I can form a whole array. So aggregation is there. So association is this integer associated with this integer array? Does it have any sort of relationship? The answer is no. It has no particular relationship with the array integer, right? We will study an example where you will see that this object has a relationship with the this object, right? So if we have a relationship among two objects, we are going to say association is there, and you can see it is not a dotted line, it is a strong solid line, which means there is a strong relationship between the objects. So there is no strong relationship between the array and this, so I can say that we have aggregation, right? So now we have studied composition and an example of aggregation also. Now let's consider a very simple example of association, right? Now let's say we have a bank, right? We have a simple bank, and let's say we have an employee. Now again we will start from composition, right? So can I answer this question? Employee is a part of bank? Yes, employee is a part of bank. Then can employee and bank exist separately? Answer is yes. One employee may work in some different bank. Employee will, if I destroy the bank, the employees will still exist, right? They can join some other bank. You can also say it this way also. So aggregation is possible. Composition, right? We have said composition is possible, but aggregation is possible. So bank and employee has aggregation. So what I can do is I can create multiple employees, let's say E1, E2, and they can aggregate with this bank, right? So I can aggregate multiple employees inside of a bank. Now let's move on to association. Do you see any relationship between these two objects? Yes, answer is yes, because employee is associated with a particular bank. So if an employee is working with a bank, he is associated with that bank. So we are going to say a strong association is there, right? So in strong association, we have a simple solid line, and we say that bank and employee are associated because they have a direct relationship, and aggregation and composition is holding true here. Now association is holding true, so we are not going to say that bank and employee has an aggregation or composition relationship. No, we always try to see where we have reached the true position. At the position association, we are still getting the condition right. So now bank is actually associated with the employees, right? So this is how we can represent different relationships. You can construct your own different examples to get these types of relationship. Now let's move on to the last part of the video, which is the final and most important, which is cardinality. Cardinality deals with the number, right? So let's say we have a bank and we have an employee, right? So you can see we have one here. So this is basically relationships. These are the lines I'm showing. Below this line, we have a number here. You can see 1. 1 means there is only one object which is related, right? 0 dot dot 1 means that 0 or 1, right? So it can be 0 or 1. So I'm going to write here 0 dot dot 1 means 0 or 1. If we have a star, it means we have many, right? So if we have a star, we have infinitely many objects, right? If we have 1 to star, it means we are going from range 1 to infinity, right? If we have 0 to star, it means we have 0 to infinity, right? So 1 is included, 0 is included. So it deals with the number, right? I will give you a very simple example so that you can see what is the meaning of this. So we will construct some different examples, and we are going to summarize all the concepts that we have studied, right? So I'm going to remove this diagram here. Now let's consider a simple example of a library and books, right? So I have a very simple exercise for you, right? So if you have reached till this part of the video, it means that you have understood UML and you have a lot of knowledge, and you are good to move to the next tutorial, which is the design patterns. Now I want you to tell me what relationship is the relationship among library and books. You can pause the video and think about the solution. So now I will give you the answer. So first is I'm going to talk about composition, right? So is library composed of books, or can we say that books are a part of library? Answer is true. Can books and library exist independently? Answer is yes, right? If I destroy the library, will the books will also get destroyed? Then the answer is no, because maybe there are a lot of books. We have a very large amount of books which were not even in the library, right? So can we say aggregation is there? The answer is yes. So I can just draw this diagram that aggregation is there, right? So I'm going to just leave some gap because we also need to write the cardinality. So we have books here, right? Okay, so now we are going to deal with cardinality, which actually means the number of objects. So how many books are there? You can see books can be many, infinitely many. So I can write infinite, right? Now we have only one library. So I'm going to write one library can be there. So I will write 1 here, right? So cardinality is 1 to infinite many, right? Now let's consider a car engine problem. We already know that in car engine, we have a composition. And let's say now we have this engine. We have only one engine, we have only one car. So now we are going to say there is a one-to-one relationship here, right? You can construct more examples where you have 0 or even more than 0, right? So let's say we have a library with 0 books. I can say 0 to many, right? It can have 0 books or it can have many books, right? Similarly, if I want the lower limit to be 1, I can just change it that, okay, a library must have one book inside it, right? Then only we will say that it is a book, right? So it goes from 1 to many. So the 0 to many and this star is exactly the same thing. You can even remove it from here, right? And you can say that this is 0 to many. So 0 to many is here. So 0 to infinite, right? 0 is inclusive, right? So here we have one or many books. We can have minimum one book and maximum infinite books. Similarly, we can have only one engine here, and here we can have only one car, right? Similarly, you can construct more examples where you can have a 0 or 1 object here, and you have more than one objects here, right? So cardinality deals with the number of objects on both sides. On this side, we are going to write the cardinality above this relationship, and on this side, I'm going to write the cardinality below the relationship, which is very important, right? So in this fashion, we will use and we will study more UML diagrams when we will deal with the design pattern. And in the next video, we will start our first design pattern where we will use this language, where we will draw the diagram representing that particular design pattern, which is the factory pattern, right? So that's all for this video. Thanks for watching.